This is part 2 in our two-part series concerning basic identity of the gamma function. In the last video, we began with this integral expression for the gamma function, and then we derived this integral. In this video, we're going to do the reverse. We will start with this integral, and from this, we'll derive the standard definition for the gamma function. So here is our integral. The natural log of 1 over x, with these limits, x goes from 0 to 1. This is, of course, natural log of 1 over x. It's the natural log of 1 minus the natural log of x. That, of course, is 0. So we can rewrite the integral as minus the natural log of x to the p minus 1 dx. X goes from 0 to 1. And then we try our substitution, saying x is going to have to be e to the some power, obviously, so we say let x equal e to the minus a, so that when we take the natural log on both sides, we get minus a over here, or a equals minus the natural log of x. And then we have this raised to a power, p minus 1, so that will equal a raised to that same power. And now from our substitution here, dx, that's just going to be e to the minus a times the differential of this exponent, that will be minus dA. So this was our original integral. If we put it in this form, this part of the integral is this. It's a function now of the variable a. dx, that is this. Now, if we're going to write an integral, though, in terms of a variable a instead of x, then we have to figure out what the new limits of integration are. So x, that's e to the minus a, and x goes from 0 to 1. These are our limits here when the variable inside the integral is x. If x is 0, a would have to be infinity. That would be then 1 over e to the infinity, which would be 0. And if x is 1, a would have to be infinity to make x 0. And if x is 1, a would have to be 0. E to the 0 is 1. So again, if a equals infinity, e to the minus infinity, that's 1 over infinity, that would make x 0. And if a is equal not to 1, but if a is equal to 0, e to the 0 makes x equal to 1. So these would be the limits for x. These are the corresponding limits then for a. So let's see if we can rewrite our integral. This minus ln of x raised to this power is a to the p minus 1, and dx is this, e to the minus a dA. Let's do this again. Here we have this raised to that power. That's a raised to the same power. dx is this, which we have here, with the minus sign out here. A goes from infinity to 0. Or we can reverse the order of the limits and take that minus sign away. This is 0. That goes away then. And that's infinity. And that is the gamma function of p, the standard definition for it. And to be clear about this, originally we had it like this. If we have this, say just for some function dx, of course that is equal to minus x evaluated at infinity 0, or here we have this minus this with a minus sign, or that would be the same thing as plus x. Either way, so that's why we were able to take the minus sign and reverse the order of the limits on the integral. But okay, then what we did in this video, we started with this form. Once we did our substitution here, then everything else pretty much just fell into place, and we were able to show that when we have this integral, we can derive this integral, which of course is our standard definition for our gamma function. Okay, hopefully that was helpful. A reminder, the playlist now for these videos is at the website, digital-university.org. If you click on where it says free calculus videos, then scroll down through there, you'll see where we have a whole section on integral functions. We have the gamma function, the beta function, and we're now going to start including elliptical functions in that same section.